What next is that let's look at something more demanding. Now we know that the theorem is true for binary random variables, so we could ask, is the proof okay for finite range random variables? That means that we assume that Z is now from omega to a finite set. Let's call it A1 up to AN. So there's a finite set of values now, not binary, but finite set of values. And we assume that Z is again sigma y measurable. These finite range random variables, there's another name. I don't like this name, but it's commonly used. They are called simple random variables. It's really a misnomer. Mathematics is full of misnomers. This is one of the misnomers because, well, imagine something with a finite range. For example, imagine the collection of all graphs with property that they don't contain a Hamiltonian cycle or something like that. This is a finite set, but you could think that there's a billion nodes, and we look at all the graphs with no Hamiltonian cycles. So there's nothing simple about that. It's extremely complicated finite set. So I would prefer calling these finite range random variables. All right. Can we prove the theorem for this case? Yes, we can. Let's look. Let's define AK to be the pre-image of the singleton set, which contains only the value AK. All right. So this is the set of omega such that Z of omega is equal to AK. That's what it is. Now we write, then we actually, I claim that we can write Z omega as a sum K from 1 to N, these values there, and then we write the indicators of these sets in this way. Is this equation, does it look clear to you, or is it like, this is always the case, so it could be trivial for you, but it could be very hard to understand why this is true. So maybe I could make a little gallop. Could you give me green light if you think that, yes, this equation is kind of clear to you, that you understand why this is true? Or give me red light if you see that, okay, please explain why this is the case. Let's say it's 3 yeses, green and red are quite close, so please give me more votes so we know what to do. Okay, red is winning, so thank you. We will explain. This is extremely important. So why is this true? Now we looked at, okay, again, we have the real line here. There's A1, A2, and let's say A3. Maybe we only have 3 values here. And let's assume N is 3 in this picture. And then here we have the omega. So we take the first point A1. We look at the pre-image by A1. What are the values where Z is mapping things to A1? So we map to A1 by Z. So that's the pre-image. A1 is the pre-image of A1, little a1, yeah. Then we have another value there, A2, and we look at the pre-image by what are the values omega which are mapped into A2. So maybe this is the set A2 here. Then this is the green part of the space. And finally, maybe there's one more color. Let's use black for the remaining. So there are values which map into A3. And maybe what is the key actually here, when you understand why this is the case. So all what remains all what remains in omega must belong now to A3. So we are coloring actually the full omega here. And the thing is that we can write omega is equal to the union of A1, A2, A3. Funnily, I got a little headache after drawing this black. I think it's a mental sensation. I thought that I was using a lot of black ink, and then I thought, okay, I will smell the black ink. So, but I need to remind me that we are in Zoom. So I should not have a headache now. These A1, A2, 3 are disjoint. So these actually form a partition. We have a partition of omega in this case, and we have 3 target values, which are the possible values. So Z must map into one of these always. Yeah. So either Z is mapping there, or finally these values are mapped into A3. And one of these must happen. So we look, okay, we have a partition. There could be n values, and one of these must happen. So actually, if you look at these indicators, so only one of these can happen at the time. So if you look, let's say case, if omega is such that omega belongs to A2, so then what is the value of k from 1 to n, ak indicator ak omega? So if you write it down, it's A1 indicator A1 omega plus A2 indicator A2 omega plus indicator A3, A3 times indicator A3 of omega. And if we assume that omega belongs to A2, so then this number gives you 1. Yeah. What does this number give you? Because they are disjoint, then this one gives you 0. Yeah. So there's nothing there. Omega cannot belong to A3 because we assume that it belongs to A2. So then this one gives you 0 as well. So what is left is actually this value here, the indicator of A1, which gives you 1. And this is A2 times 1, which is A2. So if omega belongs to A2, we get the value A2. What is the value of Z omega? Well, Z omega for omega in A2 is A2. So that's why the thing is true. Now let me ask again: is it now any clearer? Give me a green light if this is now understandable. Very good. Now I'm getting lots of green. Thank you. Let's clean this away now. So this is important, but now we know it. What did we learn? We learned extremely important formula, which is here. Whenever we have a random variable, or whenever we have a function having a finite range, we can always write it down in this form. Yeah, that's what we can do always. Right, and now let's continue the story. We assume that we have a random variable that takes on at most finitely many values, and it is measurable for sigma y. Then we denote it AK with this notation. We define these pre-images, and we learn that Z can be written as the sum of constant times an indicator function in this way. We continue, and actually what we continue is very similar to the binary case. Namely, we now note that AK, because it is the pre-image by Z of singleton set AK, and this is a Borel set, and Z was measurable with respect to sigma y. So then this set must be in sigma y. All of these 3 sets are in the collection sigma y. And we also learned that this is actually a collection obtained by the pre-images by y. So it follows that actually AK can be written as the pre-image again of some Borel set. Here. And this is again, here we have this existence because we kind of found some sets bk. And we do the same as we did previously. So we learned that the indicator AK is actually indicator of BK composition Y. Yeah. And then we look at the sum formula. Z was the sum of this constant times the indicator. So now it follows that Z can be written as the sum from K from 1 to N, constant AK indicator. Now I'm writing BK here. And let's write here omega. So we look at the value of Z at omega. So now we can write here indicator BK at point Y of omega in this way. And I'm writing here that this is the same as F of Y omega, where now F is this sum from 1 to N AK indicator BK F of X for any real number X. And that's the F that we get. So it follows that Z is F composition Y. Is this F a Borel function? It is. This is Borel function. And let's say that's homework for you to check. It's not hard. So you need to check that this F is a Borel function of this form. And yeah. And now we have a Borel function there, and that's the end of the proof here in this case, actually. So with this argument we have been able to prove the thing for the binary case, and we have also been able to do it for the finite range case. What's left? Well, what's left is the kind of all the rest, the infinite cases and the uncountable infinities, all of this stuff. So now, can we extend this to some random variables which take on infinitely many values?